All right, here we go for the mechanics example. I'm going to have to screenshot this and send it over to Paint a handful of times, but hey, it'll still work. So this particular problem tells us that a projectile is fired from a device. It leaves the launching device with a speed of Vx. And when the projectile is in the launching device, it experiences an impulse J sub p with an average force F avg. We are to assume the force becomes zero just as the projectile reaches the end of the launching device, and express our answers in terms of Vx, Jp, F average, and fundamental constants. The first thing it wants us to do is determine an expression for the time required for the projectile to travel the length of the device. So this is a momentum question. We had two objects together, projectile and launching device, and now they are separated. What we can say is, by definition, impulse is force times time. So, simply put, our time would just be the impulse given, J sub p, divided by the force given, F sub avg. For B, it says determine an expression for the mass of the projectile. So this continues onwards with the idea that impulse, by definition, is m delta v, or change in momentum. So delta v itself is going to be v final, which is vx, minus v initial, which is 0. So delta v is vx. So we have mvx equals j sub p. The mass, j sub p over vx. Let's go ahead and get C and D into here now. Yeah. For the next phase, it says projectile is fired horizontally into a block of wood that is clamped to a table so that it cannot move. Projectile travels a distance d before the block into the block before the block stops it. Again, express our algebraic answers in terms of d and the given quantities previously listed. So d has joined our known values of Vx, Jp, F average. So the projectile is fired horizontally into this. Again, as I said in the energy one, energy and momentum are so intertwined, it's impossible really to find a momentum question without energy question without momentum. So let's use the concept of work as the change in the kinetic energy. The final kinetic energy is 0 because it stops inside of the block. The initial kinetic energy is 1/2 mv squared. We just solved m, don't forget the negative. The m value is Jp over Vx. And the v value is Vx, and we square it. So when we square Vx, and we're going to divide out of Vx, the result is we'll only have one Vx left. So this will be 1/2 J sub p V sub x. And that tells us the work done. Now it wants us to derive an expression for the average force B, F sub B, exerted on the projectile as it comes to rest in the block. Again, another energy concept deals with work is force times the distance d. We just solved the work done was 1/2 Jp Vx. That will equal F sub B times d. We are allowed to use d, it said so up here. The result would be the force B would end up being, and this negative at this point isn't really relevant. You don't have to worry about it because we're trying to find the average force and it's a magnitude that we're ultimately looking for. So Jp Vx, and the 2 stays on the bottom, and a d. And that should be our average force exerted.
Now again, keyword is average force. That's why I didn't have to do any calculus to solve this. I could just jump right into the algebra. It's moving onwards to E and F. So we'll copy this into Paint, paste it here. Now a new projectile and block are used. They are identical to the first ones, but the block is not clamped to the table. Projectile is fired into the block of wood, and it travels a distance dn into the block while the block slides across the table a short distance, capital D. We are to assume the following. Projectile enters the block with a speed Vx, just like before. The average force Fb between the projectile and block is the same as we determined in part D. The average force of friction between the table and the block is F sub t. And the collision is instantaneous, so the friction force is negligible during collision. Okay, we want to derive an expression for dn, that is the distance the projectile fired into the block travels. And we want to find an expression for dn in terms of d, big D, ft, and f sub b. Okay, so the first thing is D, to remind you, is the projectile travels D into the block before it comes to a stop, as opposed to, so little d without the subscript was the distance it traveled into the block under the first given scenario. Alright, so where to begin with this? Well, first things first, we do know once again that the energy will come to some value down to 0. So we do know once again this much energy is expelled. As we solved in part C, the energy expelled is a 1/2 J sub P times Vx. So we have the 1/2 JP Vx that we did before, but the problem with this is JP and Vx aren't permitted in these expressions. So let's think about, well, what else was the work expressed as? It was expressed as FB, which was the average force we solved in part D, and times D without the subscript, because that's the distance that the bullet traveled in the block. This one is viable to use. We have FB right here, and we have lowercase d right here. So although this is a nice theory and it helps us kind of understand what's going on, it's not going to be useful in our answer. This is what we want. But this is a little bit trickier now than before, because there's two things that are doing work. There's work done by the block onto the bullet, and then there is work done on the table between the block and the table, creating friction. So what I can say is these two things, the work done block bullet combination and the work done table block combination, has to equal F sub B times D. The work done by the block onto the bullet. So what we do know is that will still be the average force we solved in part D, because it told us this. It made that an assumption. Except we're not going to use D. We're going to use D with the n subscript, because it's the new distance. This D sub n is less than this D without the subscript. Now, the work done by the table. Well, the table exerts a force F sub t across a distance, capital D. Now, our ultimate goal is to solve for dn. So, doing some algebra tricks, we would have F sub B, which we're allowed to leave it into, and told us we could here, times D minus F sub T times capital D equals F sub B times D sub n. So D sub n would be D minus FTD over FB.
And the final thing is derive an expression for d sub n in terms of d, the mass m of the projectile, and the mass capital M of the block. So I need d sub n. I'm solving for it again, but I need it in terms of d, little m, and big M. So I had to stop and restart because on F I went down the wrong path, and rather than waste your time on a video, I just deleted it and I'm going to restart. So what I'm going to do for part F is I'm going to utilize the conservation of momentum. Prior to the collision, I have mvx plus 0. After the collision, little m plus big M times some unknown velocity v. That unknown velocity v is mvx over little m plus big M. Now that tells me the work done to bring this to a stop is 1/2 times the mass, little m plus big M, times the velocity squared, mvx over m plus big M squared. This will simplify. I will end up with m squared, vx squared up top, and a 2 times m plus m on the bottom. This is the first thing that is, well, why this problem is kind of ridiculous. I'm going to factor out a 1/2 mvx squared. And what that will leave me with is an m over m plus big M. Why factor it out? Well, it's because of the terms that they want everything expressed in. So 1/2 mvx squared, we know from before, is the force exerted by the block times d. This takes us back to part C or D, I can't recall at this point, but the 1/2 mvx squared of the bullet. In order to stop it, the work done on it was FBD. D being the original distance when the block was secured to the table. So that's half of what I need, which is already stressful enough. The second half of what I need is right here. So I'll copy this and I'll paste it down. Whoops. The reason why I need that is because I also know the work done on the bullet block system is the force from the friction caused by the table times D. And ultimately, what I want to say is FB little d times M over M plus big M equals FTD. The work done is equal to the work done. Okay, so let's go ahead and solve what is FTD. Well, that equals FBD minus FBDN. And by doing that substitution, I will finally get dN into the equation that I want. FBD M over M plus M equals FBD minus FBDN. FB cancels out because it's existing in all three terms. And finally, I can solve for dN. I'm going to take the dN, move it to the left. I'm going to take this garbage and move it to the right. So d plus d times M over M plus big M. I can factor out the d if I want. 1 plus little m over little m plus big M. If you didn't get part F, I would not be overly stressed about it. That's quite the leap to get to.